Hello and welcome everyone. In this video, I will explain briefly on the Monte Carlo simulation method, mainly in relation to calculation of value at risk. And I will then provide you with an illustration using the real world data of 5 different stocks. So I will have a portfolio of 5 stocks to illustrate you the computation aspect using Monte Carlo simulation method to derive the risk at different confidence intervals given by the Monte Carlo simulation technique. But first thing first, which is these materials will be available to you through Blackboard, and for students who are abroad, they can visit my blog, Banks and Markets, click Finance, and this page will take you to various links, and you will also find topics on value at risk, where inside you will find the lecture slide as well as the numerical illustration using the real world data. So firstly, I would like to mention about a small background related to the method itself. The method first appeared in the paper by Metropolis and Ulam back in 1949, and you would know from the name that the name of the method is taken from this very famous casino in Monaco, which is one of the smallest countries in the world, but the casino called Monte Carlo is the word famous. You can play this short video to see the Monte Carlo Casino, but that's where the name is taken from. Stanislaw Ulam is considered as the first person to have originated the method. Of course, when the method was first developed, Ulam being a scientist, the method was mainly used in science in the area of atomic bombs. But then the application has wide use, not just in science, but also in different areas of science, such as biology, in order to find out, let's say, the containment of bacteria and their properties. It's also widely used in traffic management, including in finance. So several different applications, but here today we want to see how the method can be used to compute the risk, the market risk given by VAR. So one of the main ingredients, or also the foundation of the method, is the randomly generated number. As you can see in this spinning game roulette, you would not know where the ball will land, i.e. it can land in any numbers. So this will therefore take the randomly generated number. In Excel, in Microsoft Excel, there is this function equal rand, open bracket, close bracket, that will give you a value between 0 and 1, and that's what we'll be using because it's easy. We all have access to Microsoft Excel, and that's how we will see the application of Monte Carlo simulation. But basically, the Monte Carlo simulation itself is a stochastic process, which is to say that the randomly generated number is important because we do not have then control over the number that is generally randomly generated. So just to illustrate this concept here and the application of the rand function, I would like to quickly show you something in Microsoft Excel, for which I'm opening a new file. As you can see, I will first type in equal rand, and that way you will understand that this provides you a value between 0 and 1. So that's what you can get, and you could copy paste, so different numbers you can get that. So that's going to be very useful. So now what we can do is we can say multiply it by 2. So you see a value between 0 and 1 has been multiplied by 2. So sometimes it's greater than 1, sometimes it's less than 1, because value between 0 and 1 has been multiplied by 2. So what additionally you can do is, now instead of having values such as this, you want to find out a complete value as in an integer. So what you can therefore do is type in int and then everything inside parentheses, so you get 1, and if you continue start pressing F9, sometimes you get 0 or 1. So if the value is greater than 1, then you get 1. If it is less than 1, then you get a 0. So that's what the int function has enabled you to do. What you can additionally do now is times it by 2, and therefore you end up getting this. Again, you can press F9. Now you also get the value 2 sometimes, okay, or 0, 2 or 0. What you can do now is 1 minus this, so you get either 1 or minus 1 this times. So it is 1 or minus 1, you can just see it. Okay, so what we've just achieved is a value which will be either 1 or minus 1, such as this. So now let's say that you have these many numbers of values here from 2 to all the way to 53. Let's bring it further down. So we stop, let's say here 201 is where you want to end, so that you have 200 different either 1 or minus 1. So here, that's the concept is saying you can start from 0. So what you can then say is 0 is here. And then you see plus 1, minus 1 type of value is what we have achieved. What you can do now is create the cumulative type values. So therefore you just add here, so that now it is 0 plus this value 1, and therefore you get 1. So now if you double click, you will get the values all the way to 200th point. So you have achieved this. Now you may like to draw the diagram, and that's something you can do just by pressing on your XY scatter diagram. Of course, XY scatter diagram is mainly for the purpose of two series X and Y, but you can force Microsoft Excel to give you the data. So that's something you have been able to achieve. Now, if you keep pressing F9, you will see that the value changes, such as these, and so on. So what has happened here is similar to in a Brownian motion. You start with the value of 0, and this is at time t or time 0 now, and at time t plus 1, or in the end you end up getting a different value here. So again, when you repeat this, you will end up somewhere like this, sometimes here. Again, you can repeat and you are here, which is a different value again, and this time different, and this time above 0, and this time much below 0 here on the scale, and so on. But what you can do is you can still think of some kind of probability distribution, for which what you can do is draw a line just to illustrate this, what is happening, and therefore you will be able to see that this makes sense. So I've just drawn this here, and next what I will do is I'll take this, and over here I will start drawing something similar to normality distribution. Let me do it once again so that I can capture something similar to bell-shaped curve. So that's what you would expect in a bell-shaped distribution. Okay, so that's what I wanted, and I have done that. So what I meant to say here is when I will have the values, I will get different values at time t plus 1 or in the end. And if I record the values in the end that I will achieve for all those values, if I see the distribution pattern, I can then again form something similar to normality distribution. So this is in a way a small and quick explanation on the stochastic process, wherein we are assuming the fact that the random process can start at time 0 or with a score of 0, and that event can happen t number of times, and we will be able to observe the data in the end, which will still follow some kind of distribution pattern, and we can capture such distribution pattern, and that way we will be able to generalize it. That's the main concept here. Okay, very quickly, as a layman example, what you can say is when you, let's say, spray the room freshener in a room. So room freshener spray. When you do this kind of spraying in the room, what will happen is, if you are in the center of the room, then let's say the molecules of the room room spray, room freshener spray will diffuse inside the room, but at first it will concentrate in the center. So center is something like this point here, 0, but eventually it will spray all over the room, and somehow there will be equal distribution all around the room, assuming you are spraying from the middle. So that's exactly what we can say, which is the distribution will then take some pattern, and we can, in this example, for randomly generated data mainly involving the stock prices, we can assume them to be following normality distribution. So then the other thing that we need to do is generate a large number of trials or experiments, and from there find out the value at risk at the given confidence interval. The formula here given, we would like to use the stock price is this. Now in terms of the return, the e or exponential converts into natural logarithm, so therefore we can simply take this one here in order to compute the simulated return values from t to time t plus 1, simply here defined as t plus delta t. Of course, it will be easy when I will be showing you an illustration, and therefore, without losing more time, what we can do now is see how the Monte Carlo simulation approach can be applied in the context of uh, stocks, and then we can see how the value at risk can be computed. So what I've done here is I went to the Hong Kong Yahoo Finance web page and I typed in Hang Seng Index, and inside Hang Seng Index I've checked constituent stocks, and from there I have taken 5 stocks, and they come from different sectors. And you can see here in the data file that I have first obtained using Yahoo Finance the stock price of 5 different companies from within the Hang Seng Index, and they are, after finding the data individually for individual stocks, I have copied them. For example, uh, for this one, which is 10.9692 and so on, I've copied this, just the close price, 10.9692, and you can see that's the one, 10.9692. And similarly for all other 4 companies, I have the closing share price. Because that closing I don't even need to mention, this then basically means I can put their names down. So that's how I have downloaded the data just by visiting Yahoo Finance and downloaded this data. Now what we would like to do now is find out the value at risk using the Monte Carlo simulation approach. So this is what I'll be doing next 10 to 12 minutes, and we'll show you how the Monte Carlo simulation method can be applied. So first thing, what we want to do is find out the return. Now, if you see the lecture slide, what I have explained here is you can use to find out the return from the stock. You can use the natural log function. So that's what I will do here, which is equal ln the stock price today divided by the stock price yesterday. That's exactly similar to what it does here, and therefore hit enter. And this is what I have achieved for the company Hong Kong and China Gas. So I can now copy and paste it for the remaining 4 columns, 1, 2, 3, 4. This means I have now achieved for all 5 stocks, and therefore the last thing I need to do in order to compute individual stocks return is double click. So I have the return for all these time period, which is from 2015 all the way to 2020. So I have the daily stock price return of 5 Hong Kong stocks from Hang Seng Index. So now what I need to do is find out the portfolio return. So the portfolio return can only be computed once we know the weights of investment in each of these stocks. So I can quickly show you what should be the formula to find out um, the portfolio return. So portfolio return, oh, that's already there. Portfolio return formula, then you can see this is what you need. Basically, the weight of investment times the the return from investment. That's the formula here, and the total of it. Portfolio return formula. So we have the returns here, but what we don't have is the weights. So let us define the weights of investment in each of these stocks. So that then basically means I have 5 stocks, and then I can invest equally if I want to. And let's assume that I'm going to make an investment of, let's say, 100 or 1 million. So if I'm investing 1 million in 5 companies, if I want to make them equal, then I'll be investing 200,000 in each of them. So that's what I can do in order to find the weights of my investments. So that's simple because we have just applied equal weighting. So that's we have achieved. Or you can simply say 200, 200, 200 and add them together, you get 1 million. This in terms of percentage therefore becomes 20%, which we all understand, and that's how you can achieve 20%, which basically means the total is going to be 100%. That's what you get here, and if you prefer you can convert them into percentage as well. So now portfolio return basically requires the use of this formula, weight times the return. So basically what you can therefore do is apply the formula sum product, and what it does is it multiplies the weights with the return. So what you can do here is as soon as you finish typing sum product, you can lock this and comma the returns from each of them. So now you have the portfolio return, which is this number here. It is same as saying the return times the weight of the first investment. Return from the second stocks times the weight of the second. And then the third with the third weight. And then the fourth company's return times the fourth company's investment weights, and finally the fifth times the fifth company weight of investment. So you get the same number here as you can see, but you save your time by using the sum product function, which is easy and straightforward. So we can just move ahead with this. Now your job is simply to double click so you have portfolio return for all these time period. So now you have found from your portfolio the daily portfolio return. Next, what you need to do is find out the information needed by this formula. So what I will do for convenience, I'll copy this and paste it here so that you can see what I have and why I am obtaining the values that I am bringing here. Okay, so again, the emphasis here is we need these. Okay, so let's start with the investment, which is basically the stock price at time 0. What is it? So that basically means your total investment amount, which is 101 million. And then what you need after this is your average portfolio return. So average daily portfolio return. So that is going to be equal average open bracket all these portfolio return, and that's it. So that's the average daily portfolio return, which is what you have just achieved. Let me enlarge so you can see this. Then you would find average daily standard deviation of portfolio return. So standard deviation of portfolio return, and for that it is now simply this value here, but you just change the information to stdev.s, so that's the standard deviation computed. So basically the sigma here in the formula is standard deviation, and that's what you have. But if you see here in the formula, you will see that there is mu here, which is basically the average return, but you can annualize this. So then this basically means you can find out annualized return, which is going to be your daily return. So 1 plus the periodic return power, this is daily, and assuming 252 number of trading days in a year, you can have power 252 take away 1, so that will give you annualized return. And similarly you can find out annualized standard deviation, which is again now equal this times square root of 252. So that's what you obtain. So you've got now standard deviation annualized, which is this, but what you don't have yet is your k, and your k is called the expected return, and your expected return is basically the annualized return take away half of your variance, which is standard deviation square. So that's expected return, which is what you have computed just now. And the final item you need is the time increment, which is t, and assuming number of days equals 252, what you can do is 1 over 252, and that's what you needed. So you have now everything that you need as per this formula. So now you can proceed on this side. Let's make use of this space on this side. So what you need, I will write here. First thing is, let's say the number of simulation trials that you want to generate. So let's say the first trial, which is number 1, and the second trial will be number 2, and so on. So as I explained, we need to have some assumption related to probability distribution. Let's assume the normality distribution, but we need the probability there. Again, the probability can be computed using the rand function. So here I'll just type in rand, open bracket, close bracket. So that basically means you are aiming to do this so that you get the value. Now this rand here needs to be converted into the normality distribution, and assuming the data follows a normal distribution pattern. So therefore what you do is equal norms. Now norms that standardize the distribution INV. So it is, you can see there is S for a standardized normal distribution. Okay, standard normal distribution, and then open bracket, the probability is just this randomly generated number here. So that's what you have done. And the final item here is going to be the formula, which is this. So what you therefore need is equal your expected return is k, that's the number here, make sure you lock it because this is not going to change, times the time increment, which is this number here, again make sure you are able to lock it, and then this is about the fact that the return, uh, the simulated return we're trying to find is the relationship between return and risk. So you've done the one for return. Now in terms of risk, it is going to be annualized standard deviation, which is this, again lock it, and then you need this error term epsilon, so that is something comes from this norms inv given value, and that's something you won't be locking. And then the final item is the square root of your time increment, which is here, again lock this number, close parenthesis, so you've got everything that you needed, so hit enter, so you get this value here. So basically what you have identified here is the use of this formula. So I will just say this is what you have done. Okay, maybe it's easy for you if you copy this and put it somewhere on the top here. Let me do it, bring it up, let me insert, oh it didn't copy, let me do it again, let me insert some rows here so that there will be space for me to pull this formula above, and now what you are saying is the item here basically represents the use of the formula, which is this. So that's what you are doing here, the formula, all of that. Okay, so that's what you have been able to compute. Now you're nearly towards the end. What you need to do is compute a large number of experiments. So compute a large number of simulated trials. So you need to define that. Let's say that we want to go from here all the way to 100, so that basically means R112, and that will be here, and therefore I can take this up, copy and paste down, so I have 100 repeated simulation that I want to find out, and I can just double click here and I get all these values. Remember again what is happening with norms INB. If you remember, this is just giving you the JD score. For example, if this was, let's say 5%, you would know that this will be minus 1.6485, and that's what you can see here. So that's what we have been doing. Hence we can say that the randomly generated numbers here have been converted into the distribution such that it takes the form of normality distribution. So let's change it to again rand open bracket close bracket, so that it's a value between 0 and 1, and we have computed this. Now the last step here is to compute the Monte Carlo simulation given VAR. So I will do it for different confidence interval, 90%, 95%, 97.5%, and 99%. So what this basically means is 90% of the time the market will remain normal, but 5% we don't know, so that, sorry, 10% we don't know, therefore that's the uncertainty given by the alpha. So that's confidence interval, and that's the probability value, we can call it alpha for now, or P, okay, just for the probability, probability of uncertainty in the case of VAR, T of market being abnormal or uncertainty. Yeah, that's what we have said. Now we can find out Monte Carlo simulation given VAR, and for this VAR in percentage first. Yeah, so for this what you need to do is simply apply the percentile function. This has come down now because I've played around a little bit, haven't I? So I'll keep it here like this. So now what you need to do is equal percentile. By definition, this is .exe is the correct one. So then you define, you have the array here, which is from this point all the way percentile.exe, and then we just need to come here and all the way down to that 100 comma your this uncertainty close bracket, hit enter, so you get this value here. And now if you can lock these cell references, what will happen then, you will be able to capture the same cell reference each time. So you have the Monte Carlo simulation given VAR for all the confidence interval, and this is something I'll say in dollar or in pound or in Hong Kong dollar. And therefore now what I need to do is multiply this with the investment amount, which you know here is 1 million. So that's what I can as well lock, so I get this. So what we can now say here is we can even change it to ABS so that we don't get a negative figure, because when we report and say the Monte Carlo simulation given VAR is 12,608, we do not want to say that Monte Carlo simulation given VAR is minus this, because when you are saying this is about loss, so you don't want to say loss is minus 17,000, you just say loss is 17,000. So therefore it makes sense that we put an ABS here, so you get this value. Now remember, let's focus on 95%, and you can remember how many simulation trial have we got? Only 100 of them. So is it going to give us the best result? The answer is no, because as explained in the slides, a large number of repeated trial is important. Okay, so with that in mind, what you can do is obtain these values again, but for large number of repeated simulation trials. So you don't stop at 100 this time, you stop at, let's say, 1000 or 2012. So 2012, 2012, let's see, where do you go? And then you copy and paste all the way down, so you get to 2000. So now what you do is also apply these all the way to 2000. So you know that 2000 is giving you 2012 as your row number in this file. So what you can do now is over here, you can change the cell reference to 2012, 20. So now you can copy it across all the confidence intervals, and this on this one you have 100 simulation trials. Here you've got 2000 simulation trials. So now again what you can do is find out Monte Carlo simulation given VAR in dollar, and this time your simulation has 2000 numbers of simulation trials, and that's what you have done. I can again lock this, and therefore I can now drag it along. So I've got these values. Of course I forgot to put ABS, and that's what I have just done now. and that's 15,000. So that's what the number I have received. Now we can focus on these two values, and you will see this is, I will put green, and this I will put, let's say, red. And when I will change or when I will press F9, you will see the green is now 21,000, 20,000, but the red has gone down significantly to 16. Again, the green is around 20,000, again 20,000, 19,000, but you can see the red is 16,000, 21, 27, but the green has never gone below 19 or above 21. So that in that case slightly above 21, but fairly between 19 and 22,000, whereas the one wherein we had only 100 simulation trials, it fluctuates a lot more widely as compared to the one below in green. So therefore, it is important to have a large number of simulation trials while applying Monte Carlo simulation method. So this is all about the application of Monte Carlo simulation in the context of a portfolio consisting stocks. But what will be good is we compare this result for VR given by historical simulation and variance covariance approach, and see if there are any differences, and then we'll be able to find out, we should be able to find out what is causing that difference. But for this video I will stop here. It has been a video that's slightly longer than what I had thought, but it's good that we have taken our time to explain step by step the demonstration involving VR computation using Monte Carlo simulation method. So thank you very much for watching this video.